All right, today we're diving into a really powerful algorithm, one that's used for everything from solving puzzles to navigating huge social networks. It's called depth-first search, or just DFS for short, and its whole strategy is, well, it's as simple as it is aggressive. You just pick a path and go as deep as you possibly can.
So let's imagine this for a second. You're suddenly dropped right into the middle of a gigantic maze. You've got no map, zero hints. How do you even begin to find your way out? This right here, this is exactly the kind of problem that algorithms like DFS are built to solve.
You can try a really bold approach. Forget about carefully checking every single turn nearby. Instead, you just pick one path, any path, and you follow it relentlessly. You just keep going deeper and deeper and deeper until you either hit the exit or you hit a dead end. That, right there, is the core idea behind depth-first search.
Now, technically, DFS is what we call an uninformed search technique. And look, uninformed isn't a knock on the algorithm. It just means it's kind of like a blindfolded explorer. It only knows about the immediate steps it can take from where it's standing right now. It has no bigger picture, no compass pointing to the goal. It just has to commit to a path and see what happens.
Now, every great strategy needs the right tool, right? Well, for depth-first search, its secret weapon, the thing that lets it keep track of where it's been and where to go next, is a really simple but powerful data structure called a stack.
So what is a stack? Seriously, just picture a stack of plates in a cafeteria. When you add a new clean plate, you put it on top. And when you need a plate, where do you take it from? The top, of course. The last plate you put in is always the first one you take out. This whole last in, first out, or LIFO idea is the engine that makes DFS run. And seeing this comparison really highlights what makes DFS so different from its cousin, breadth-first search, or BFS. While DFS uses that stack to dive deep, BFS uses a totally different tool called a queue, which works more like a line at the grocery store, to explore things one level at a time. This one little difference in their toolkit creates two completely different ways of exploring the exact same maze.
Okay, theory is great and all, but let's actually see how this works in practice. We're going to walk through a simple example, step by step, to really watch DFS do its thing and navigate a simple tree using its stack. All right, we start our journey at node A. From here, we've got two choices. We can go to B or C. DFS sees both of them and adds them to the stack to remember them for later. You can see B goes in first and then C gets placed right on top of it. Our path has officially started. Now remember that LIFO principle? Last in, first out? C was the last node we added, so it's the very first one we're going to explore. We pop it off the stack and we travel to it. Now, from C we can see nodes F and G. So what do? We add them to the top of the stack. Our path is now A to C, and as you can see, we're going deep. The algorithm just keeps pushing forward with this single-minded focus. G is now on top of the stack, so we pop it off and go there. But, look at G. It's a leaf node. It has no kids, no other paths to explore. We've hit a dead end. So, what happens when you hit a dead end? Is the algorithm just stuck? Nope. This is the crucial part, backtracking. Since G didn't lead anywhere, the algorithm goes back and checks its memory, the stack. What's the next item on top? It's F. So it pops F and explores that path instead. This ability to backtrack is what lets DFS escape those dead ends. Okay, so after exploring F and finding out it's also a dead end, the entire branch that started with C is now totally exhausted. So the algorithm backtracks again, looking at its memory, the stack, for the next option. And what's been sitting patiently at the very bottom of that stack since the beginning? Node B. We finally pop B off the stack and start exploring a whole new part of the maze. And this whole process really shows you the signature of depth-first search. It's not a straight line, is it? The algorithm fully explored that entire path down from C, hit two dead ends, before it ever went back to even consider the path that started with B. This deep-diving backtracking adventure is what makes DFS, well, DFS. But as you probably notice in that example, this aggressive go-getter strategy isn't without its risks. In fact, its greatest strength, that relentless determination to go deep, is also the source of its biggest, most dangerous flaws. So there are two huge risks with DFS. First, it's considered incomplete. In plain English, that means in certain kinds of mazes, like one with a loop, it could get trapped and literally never find the exit even if it's just one step away. And second, it's non-optimal. It's not guaranteed to find the best path, it's just guaranteed to find the first one it stumbles upon.
Let's dig into that incomplete problem for a second. Imagine a path in a maze that just loops back on itself, a big circle. Because DFS is programmed to always go deeper, it can get caught in that cycle and just run around in circles forever. It would never backtrack to find the real solution that might be waiting on another path.
And that leads us right to the second problem, being non-optimal. This quote from one of our sources really sums it up perfectly. Just because DFS finds an exit doesn't mean it found the best exit. It might drag you on some long, winding, scenic route just because that's the branch it decided to explore first. And this table just makes it painfully clear. DFS might dive down one branch and find path A, a solution that takes 10 steps. It stops. It reports success. I found it. But in its haste, it completely missed path B, a much shorter 4-step solution, because it never even got around to exploring that branch.
So if it can get stuck in loops, and it doesn't always find the best answer, you might be asking, why on earth do we even use it? Well, despite these flaws, DFS is a cornerstone algorithm for a few really good reasons. It's simple to code, and more importantly, it is incredibly efficient with memory. And for problems with billions of paths, that's not just a nice-to-have, it is absolutely essential. When computer scientists talk about efficiency, they use this idea called time complexity. It's really just a formal way to describe how much longer an algorithm takes to run as the problem gets bigger. For DFS, the time complexity is often written as O of b to the power of d. It looks a little scary, I know, but it tells a very simple story about where DFS spends all its time.
Let's just break that down. B is the branching factor. That's just how many choices you have at each step. And D is the depth, how deep you have to go to find the solution. What this formula tells us is pretty critical. The search time can explode exponentially the deeper the solution is. This is why DFS can be a huge gamble on very deep problems. The time to find an answer can become astronomical. And that really brings us to the main takeaway here. Depth-first search is all about a trade-off. You give up the guarantee of finding the absolute best solution, or even finding any solution at all in some tricky cases. But in return, you get an algorithm that is often way faster and needs a lot less memory than something like BFS, because it only has to remember one path at a time.
Which leaves us with a final question that honestly goes way beyond code. The logic of DFS forces us to think about a really fundamental dilemma in all kinds of problem solving. When is getting a good enough answer quickly more valuable than waiting for the absolute 100% perfect answer? Something to think about.